Good afternoon, everybody. Just let me know if you all can hear me, please. All right, cool. Thanks for the feedback there. All right. Um, all right. So in this session, what I'm going to be focusing on, um, in terms of the broad topics that CXE indicated, right? Um, they said you're going to get the mole concept and acids, bases, and salts, right? Based on my experience, they are referring to question 1 here on the paper, and I'm assuming that most of you have seen what an exam paper looks like, right? What that means is that the question 1, sorry, is typically worth about 25 marks, right? And there may be some calculations inside of there. There are various types of questions they can ask in the question 1, but the fact that they said mole concept, acid, bases, and salts, this is what I'm going to be focusing on, right? I know a lot of students, they get scared when it comes to moles, right? And the thing is, for some students, yes, it's a bit difficult, right? But it's not as bad as you think, guys, right? In school, sometimes they try to teach you formulas in order to help you with the moles. I can safely tell you that I have never ever learned off a single formula for moles, right? I have never done that in Form 4, Form 5, up to Form 6. I got the highest mark in A-level chemistry in Trinidad, and I have never learned off a single formula for moles, right? What you need to understand when it comes to moles is to try to understand what is actually taking place when you are mixing substances or when things are reactive, right? That's what you need to pay attention to. So, let's see. So, I made up a few questions here for us to just take a look at first before we do any exam type questions, right? Even though this is essentially what could be asked in the exam, right? Now, here's what we have here. We have a student, they wanted to determine the concentration of a solution of sodium hydroxide, right? So you have a solution of sodium hydroxide and we don't know what the concentration is. So that's unknown to us, right? Now, on the other hand, you have 25, what he did, he placed 25 cm cube of sodium hydroxide in a conical flask with an indicator, right? Now, you all are writing an exam just now. I'm hoping that you all actually did a titration in the lab before, right? So a titration is something that is very common and you have to be able to do a titration. And what we do, we try to determine the concentration of an unknown, of a substance that we know, but we don't know the concentration, right? Now, when it comes to titrations, there's something called a standard solution, right? That could be an exam question. What is a standard solution? A standard solution in chemistry is a solution of known concentration, right? So if you see that question in the exam, that is what they want for the answer. A standard solution is a solution of known concentration, right? So in this particular question here, we don't know what the sodium hydroxide is, but we're going to titrate the sodium hydroxide with hydrochloric acid, which we know what that solution is, that concentration is, sorry. So if we look carefully here, the concentration of the hydrochloric acid is 0.15 mole per dm cube, right? And what we are saying is that you require 20 cm cube of hydrochloric acid in order for neutralization to take place. Now, try to make sure you understand what's happening here. So in a titration, we have a conical flask, right? And we use a pipette to put some, in this case here we're using sodium hydroxide. So make sure you understand what's happening here. So this is sodium hydroxide we are adding to a conical flask. That's what it looks like, right? And to do that, we're going to use something called a pipette, right? So that's the tool that looks like this, right? So a pipette gives you a fixed volume of a substance. So what you do, in most schools, they either use a pipette to suck the sodium hydroxide into the pipette, or if you're in a fancier school, you may have a rubber bong to allow you to fill the pipette with the sodium hydroxide, right? Either way, we need to fill the pipette with the sodium hydroxide. In this case, we are using 25 cm cube in the conical flask. So what you're going to do here, so this here is 25 cm cube, right? In the conical flask, what we normally do, we add an indicator to the sodium hydroxide, right? So there are different indicators that you may have met along the way. So we have things like metal orange, we have screen metal orange, we have phenolphthalein, right? There are various indicators we can use in order to determine the endpoint of a titration, right? And the endpoint of the titration is when all of the acid has reacted with all of the sodium hydroxide, right? Now, what else do we know? So then we're going to add the hydrochloric acid to the sodium hydroxide. Now, in order to do that, what we use a different tool, something called a burette, right? So this here is my burette that we're going to add my acid with, right? So this is HCl, right? We don't know how much HCl as yet we need to add, but what we do know is the concentration of the hydrochloric acid, which is 0.15 mole per dm cube, right? So this here is the concentration of my hydrochloric acid, right? And this here is what I said we call the pipette, right? So the pipette is used to add a fixed volume of a liquid, right, to the conical flask in this case here. So I'm just trying to paint a picture for you all so you understand what is being added to what, right? So you have the sodium hydroxide in the conical flask, right? You put an indicator inside of it. That's going to allow us to determine the endpoint. Now the indicator will be a color in alkali. In an alkaline substance, it will have a particular color. In acid, it will have a different color. So as soon as you reach the endpoint of the titration, there's going to be a color change. So you are continuously adding the hydrochloric acid to the sodium hydroxide until we get a color change, right? And the whole objective here is to actually find the volume of acid we require in order to do so, right? So let's see now. Make sure you don't ask me anything. Right, so they did the titration, right? And they realized 20 cm cube of the hydrochloric acid is required for complete neutralization, right? The first part, typically CSEC might ask you to write an equation, a balanced equation by the way, in order to show what's happening. So you're reacting sodium hydroxide and hydrochloric acid. This sodium hydroxide is an alkali and the hydrochloric acid, well, it's an acid. So you are adding an acid and an alkali. So my products will be salt and water, right? So for part A, you are adding sodium hydroxide. Now please, you all need to get into the habit of writing your state symbols. So it's aqueous in this case, sodium hydroxide, plus hydrochloric acid, right, which is aqueous as well, right? Now you are adding an alkali plus an acid. There are two products that you will get. You will get a salt. In this case, I'm going to get sodium chloride as my salt. So it's NaClAq because it's going to be in solution, plus water. Water is always going to be produced when I add an alkali to an acid, right? And this will be liquid here, right? And what you need to do, you need to make sure that your equation is balanced. If your equation is not balanced, guys, then when you do the mole calculations, you will get it wrong, right? So that equation needs to be balanced. If I look at this equation, I have 1 mole of sodium here, 1 mole of sodium here. So that's good. In terms of oxygen, I have 1 oxygen on the left, 1 oxygen on the right. So that's okay. In terms of hydrogen, I have 1 here, 1 here. So therefore I have 2 hydrogens on the left hand side, and on the right hand side I have 2. So the hydrogen is balanced. Then you look at the chlorine, you have 1 here and you have 1 here. So as it stands, right, the equation is balanced, right? So as it stands here, the equation is balanced, right? Now, this is a well-known equation, so please make sure you know this equation, right? Sodium hydroxide plus hydrochloric acid, you get sodium chloride plus water, right? So you might typically get maybe 1 mark or 2 marks for that. The next part now, part B. Calculate the number of moles in the 20 cm cube of hydrochloric acid. Now remember, you did the titration and you use the burette to figure out how much hydrochloric acid we needed, right? And we got this, we got 20. So when you did the experiment, you got 20. And I want you to work out how much moles is in that 20. Now, you know the concentration of the hydrochloric acid. It is 0.15 mole per dm cube. So, let's do that. So, the acid, the HCl, right, is 0.15 mole per dm cube, right? That's my concentration of the hydrochloric acid, right? Now, what does that really mean? 0.15 mole per dm cube. You all need to know that 1 dm cube is actually equal to 1000 cm cube, right? I'm going to make use of this here. So if my concentration is 0.1 mole per dm cube, that tells me something. That says that in 1000 cm cube, right, of solution, I have 0.15 moles of hydrochloric acid. That is what that is telling me. So I'm going to write a statement along those lines. So I'm going to say 1000 cm cube, right, contains 0.15 moles HCl, right? That is what this is telling me here. That tells me that 1000 cm cube contains 0.15 moles. That's what that is telling me. The next thing I need to do now, remember the question is asking how much moles do we have in 20 cm cube of the acid. So what I'm going to do is, therefore 20 cm cube, right, contains, so I've taught this in my online classes many times. What I'm essentially doing here is cross multiplying. I need to take this 20 multiply by the 0.15, so it's 20 multiplied by 0.15, and then I must divide by this number here, which is 1000. So I'm cross multiplying. If you're wondering what I'm doing, I'm taking 20 by 0.15 and divided by 1000, right? So let's see, I think I do have my calculator up. Yeah, I do. Right, so this is the typical calculator that I use for all my subjects that I teach, maths, chemistry, and physics, right? So let's see, what do we want to work out? It's 20 by 0.15 over 1000. So we're going to say 20 multiplied by 0.15 divided by 1000, and what you're going to get is 0.03, right? That's what you're going to get there. So 0.003. So you're going to get 0.003 moles HCl, right? Now that calculation there is pretty straightforward. For all you know, they may give you either 1 or 2 marks for that calculation, right? So that's part B, right? So just like that, we've completed part B. Now in part C now, they said calculate the number of moles in 25 cm cube of sodium hydroxide. Now we don't know the concentration of the sodium hydroxide, we don't have that information. So what we have to do, we have to use our equation in order to figure that out, right? That's what we have to do. We have to use our equation in order to figure that out. Now, this is the part that some students have trouble with. So this is part C. I'm going to just write back what the equation was. It was NaOH, right? And I'm going to put the state symbols this time, right? Plus HCl, and that produces NaCl plus H2, right? That's my equation. Now in part B, you worked out how many moles of the hydrochloric acid you had, right? Which was 0.003. So according to this equation, once it's balanced, it tells me something, guys, right? In front of the sodium hydroxide, there's no number there. That number is actually taken as 1, if you're not seeing a number there. In front of the HCl, there's no number in front of it, but we're going to take that as a 1. In front of the sodium chloride, there's no number in front of it, so there's a 1 there. And in front of the water, there is a 1 there. Those numbers that I've written down there has to do with the amount of moles, right? So according to this equation, right? According to this equation, 1 mole, right, of HCl reacts with 1 mole NaCl. I'm sorry, HCl. 1 mole of, sorry, NaOH, right? 1 mole NaOH. So 1 mole of the hydrochloric acid is going to react with 1 mole of the sodium hydroxide. But you just worked out how much moles of HCl we had used in this particular titration. You had used 0.003 moles of HCl. So therefore, this is what you're going to say. Therefore, 0.003 moles of HCl, right, will react or reacts with, right, in this particular instance, it's a 1-to-1 mole ratio. So if 1 mole of HCl react with 1 mole of NaOH, it means that 0.003 moles should react with that same amount. So therefore, this should be 0.03 moles NaOH, right? So the question asks, how much moles in 25 cm cube of the sodium hydroxide? Remember, at the start of the titration, you had used the pipette to transfer 25 cm cube of NaOH. So in that 25 cm cube, that is how many moles I have there. So you could say that 25 cm cube NaOH contains, right, this answer that we just got here, 0.003 moles, right? So this is my answer here. That's it. That's the answer for part C, right? Now I hope you guys following what I'm doing here, right? Right, so this is part C. The next part we're going to work out is part D. Calculate the concentration of the sodium hydroxide in mole per dm cube. Right, now this is typically how we get an exam question on titration here, right? But what they will do, they will give you pictures of the burette, and then they'll ask you to take measurements, right? So we'll do a few of those questions just now. So they want the concentration of the sodium hydroxide in mole per dm cube. Now here's what you do know. You do know that 25 cm cube of NaOH contains 0.003 moles, right? Now whenever they ask you to find the concentration of something, we need to find how many moles in 1,000 cm cube, right? So part D, this is what we have to do. So we know that 25 cm cube, right, of NaOH contains 0.003 moles, right? That's what we know from part C. All we really need to do here now is to work out how many moles we have in 1,000 in order to determine the concentration, right? So therefore 1,000 cm cube of NaOH, right, contains, and you're going to cross multiply. Almost all the mole calculations we're going to have to cross multiply. You're taking this number, multiply by this number, so it's 1,000 multiplied by 0.003, and then we're going to divide by 25. Divide by 25, right? Again, I'm going to use my calculator in order to do that, right? So multiplying this by 1,000, multiply by 1,000, you get this, and then you divide by 25. and what you're getting as a concentration is 0.12, right? So you're getting 0.12. So this here is 0.12 moles, right? So therefore, the concentration, so by the way, if you don't want to write the word concentration in chemistry, right? If you put, in this case, sodium hydroxide in square brackets, that actually means concentration, right? So the concentration of the sodium hydroxide is 0.12 mole per dm cube, right? You write all the words if you want, but this is just shorthand I'm using here, right? So what I've done, I've worked out the concentration of the sodium hydroxide, which we did not know what it was at the start of the titration, right? So we worked that out. And then the last part of the question now, which is something that they typically ask us, they can ask you, calculate the concentration of the sodium hydroxide in gram per dm cube. So they want you to convert from mole per dm cube to gram per dm cube. And that is something very, very straightforward to do. All we need to do, you need to find the molar mass of sodium hydroxide. So sodium, what I've done here, I've given you the relative atomic mass of these things. Sodium is 23, oxygen is 16, and hydrogen is 1, right? So to find the molar mass, which is the mass of 1 mole of sodium hydroxide, it's going to be sodium is 23 plus 16, right, plus hydrogen, which is 1, and that, I think that should give us what, 40, I think, 23 plus 16 plus 1. Yeah, that'll give us 40, right? So the relative atomic mass, right, or the relative molar mass of sodium hydroxide is 40 grams, right? So all you need to do is to convert the 0.12 into grams. So 1 mole, right, NaOH, right, has a mass of 40 grams, right? So therefore, you need to work out for 0.12 mole NaOH, right, and we cross multiply. So this is 0.12 multiplied by 40 divided by 1, and that's going to give me, so 0.12 by 40 divided by, well, right, so this is 4.8, right? So this here is 4.8, right, grams. So therefore, the concentration of the NaOH in gram per dm cube is going to be 4.8 gram per dm cube, right? Right, so somebody asked me if the ratio is different, right? So the second example I'm going to give you all, the ratio is different, right? So the second one I'm going to do, the ratio is different, right? So this is a typical exam question, guys, right? Typical exam question. So I'm going to do a second one before I actually look at an actual past paper here, right? Remember, let's read it through, make sure I didn't make any mistakes when I typed it up. Student potassium hydroxide. Alright, so again, right, it's very similar to the last one, but what I've done, I've changed what the reagents are, right? So in this particular case, the student is interested in figuring out the concentration of something called potassium hydroxide, right? So potassium hydroxide is this formula, KOH, right? So you can use potassium hydroxide in some titrations, right? He placed 25 cm cube of the potassium hydroxide in a conical flask. So very similar to what we did just now, you're going to have a conical flask, right? And you're going to place 25 cm cube of the potassium hydroxide. So this here is 25 cm cube of potassium hydroxide, which is KOH. In a conical flask, you add the indicator, right? And then you're going to titrate with sulfuric acid. So I change the acid this time. It's sulfuric acid. So you're going to add sulfuric acid, which is H2SO4. So you all need to be familiar with your formulas for your different acids. So sulfuric acid is H2SO4, and you know what the concentration is. It is 0.2, so it is 0.2 mole per dm cube. That's my concentration of my sulfuric acid. And what I'm telling you is that when you do the titration, 22 cm cube of sulfuric acid was required for complete neutralization. So this here is 22 cm cube, right? So now let's see if we can answer the questions. So part A, write a balanced equation for the reaction between potassium hydroxide and sulfuric acid. So in part A, potassium hydroxide is KOH, and this is aqueous because it's in solution, plus sulfuric acid, which is H2SO4 aqueous, right, produces. So when I'm adding an alkaline to an acid, right, just like in the previous question, we're going to get a salt and we're going to get water. So the salt in this case will be potassium sulfate, right, which is K2SO4 aqueous, right? Now, you all need, as one of the first things that you all should have learned in chemistry, is how to write chemical equations, right, and how to balance equations. That's the first thing I normally teach my class, right? Make sure you can write equations and make sure you can balance the equations, right? And you need to be able to write formulas of substances. So I'm reacting potassium hydroxide and sulfuric acid, so my salt is going to be potassium sulfate, right? Plus, we're going to get water, so plus H2O, liquid, right? Now if you look at the equation properly, you realize, wait a minute, it is not balanced because I have one potassium here, but I have two across here. So this equation as it is, right, we are not as lucky as in the first question, but this equation is not balanced. So let's see if we can balance that. If I put a 2 in front of it, let's see if that makes it balanced. So I have 2 potassium on the left, I have 2 on the right. So potassium is okay. If we look at the oxygen, you have 2 here and you have 4 here. So that gives me a total of 6. When you go on the right hand side, you realize, wait, I have 4 here, but if you look at this, I only have 1 on this side. So that's 5 oxygen on the right hand side. So therefore, I need to put a 2 in front of this to help us balance it. So now the oxygen is balanced on the left and right. In terms of hydrogen, you have 2 here and you have 2 here. So that's 4. And on the right hand side, we have 4. So as the equation stands, it is balanced, right? So this is my balanced equation for this particular reaction, right? Now, like I said, if you all make a mistake in balancing equation, right, chances are you're going to get the question wrong, right? That is important. Now, let's see what do we want to do now. Right, so we have this. So that's my balance equation. Let me just clear up some things here. So let's erase this, erase this. Right, so that's my equation, it's balanced. Now let's see what we want to do now. In the first part, we want to calculate the number of moles in 22 cm cube of the sulfuric acid. So you know the concentration of the sulfuric acid, it is 0.2 mole per dm cube. So this is part B. And the sulfuric acid is H2SO4, right? And that is, how much we said? 0.20 mole per dm cube, right? So 0.20 mole per dm cube. Right? That's my concentration of my sulfuric acid, and we use 22 cm cube of the sulfuric acid. So therefore, I need to put this somewhere here, right? So I use 22 cm cube, right? And the question is asking what or how many moles do we have in this 22. So you know the concentration, right? So therefore, we can say that 1000 cm cube of sulfuric acid contains, right, 0.20 moles, right? So I got that information from this. Once you know the concentration, you know how much moles we have in 1000. So therefore, we need to work out for 22. So therefore, 22 cm cube of H2SO4, right, contains, and we're going to cross multiply again. So it's going to be 22 multiplied by 0.20 over 1000, right? So some students, when they work this question, they forget to divide by 1000. So please try not to make that mistake in the exam, right? So I'm going to take 22. So let's use the calculator here. 22 multiplied by 0.2 equal divided by 1000, and I'm going to get 0.044. So 2 zeros and 2 fours. 0.0044, right, moles. Right? So that's it. That's my answer for part B. Right? I knew the concentration, I know the volume of acid that I used, which was 22. Right? Now, part C now, we started to talk about the potassium hydroxide. That's the one we don't know the concentration of. But we know we use 25 cm3. So here's what you have to do for that particular one. In that particular one, we have to use our equation in order to figure out how the potassium hydroxide reacts with the sulfuric acid. Right? So let me just write back the equation on this side here. It was 2 KOH plus sulfuric acid, which was H2SO4, and that was producing K2SO4, right, plus 2H2O, right? That was my equation here. Now, according to this equation, right, so somebody asked me a little while ago, what if the mole ratio is different? So, look at this. In front of the potassium hydroxide, you have a 2 here. In front of the sulfuric acid, we have a 1 there. You're not seeing the 1, but there's a 1 there, right? So 2 moles of potassium hydroxide reacts with 1 mole of sulfuric acid. That is what the equation is telling me, right? Now, let's look and see what we're trying to work out. We're trying to work out the number of moles of potassium hydroxide. Now, when I'm writing my statement, because I want to work out number of moles of potassium hydroxide, my statement has to be written in such a way that potassium hydroxide is on the right hand side. So let me show you what that means. It means, according to this equation, 1 mole of sulfuric acid, right, reacts with 2 moles potassium hydroxide. So I'm getting this statement straight from this, That's where I'm getting that statement from, right? According to that equation, 1 mole of sulfuric acid will react with 2 moles of potassium hydroxide. But in the previous part of the question, you worked out how much sulfuric acid we had, which was this figure here, 0.0044. So you're going to say, therefore, 0.0044 moles of sulfuric acid, right, reacts with, right? Now, since you know the mole ratio is 1 to 2, what you have to do here, you have to take the 0.0044 and multiply by 2. I'm going to divide by 1, right? I know dividing by 1 doesn't make a difference, but I try to emphasize this because when students start to do a set of mole calculations, they need to understand what they're doing. So when you multiply this, you're going to get 0.0088 moles potassium hydroxide, right? That's what you're going to get, right? So therefore, and remember we use 25 cm3 of the potassium hydroxide. So therefore, 25 cm3, right, of KOH contains 0.0088 moles. Right? So I'm only able to figure out this piece of the question by using my equation, right? So that is part C. Now part D now, which is the whole purpose of the titration, is to find the concentration of something that we don't know, which is the potassium hydroxide. And we want that in mole per dm cube. So all we need to do, you're almost there, because you know that in 25 cm3 you have this amount of moles. So all you need to do is to work out for 1000, right? So that is, what part of the question is that? That's part D, right? So that's part D. So 25 cm3, right, of QH, right, contains what you just got, 0.0088, 0.0088 moles, right, Therefore, 1000, because when you're working out concentration, you're really working out how many moles we have in 1000 of KOH contains, and you cross multiply. So it's going to be 1000 multiplied by 0.0088 over 25, right? So let's do that. So let me pull back up the calculator here. So that is 1000 multiplied by 0.0088. Oh boy, hold on. Extra zero there. Right, 0.08 divided by 25. So divide by 25, and you're going to get 0.352. So 0.352. So this is 0.352 moles. Right? So therefore, remember the question asks for concentration. So the concentration of the potassium hydroxide. So like I said, when you use square brackets around a formula, that means concentration. So this is going to be 0.352, right, mole per dm cube. That's my concentration of the potassium hydroxide, right? And then the last part of the question, we want to convert that concentration into gram per dm cube. That's what we want, right? And I've given you the relative atomic mass of potassium, oxygen, and hydrogen, right? So, potassium hydroxide, we need to work out the molar mass, right? So that is going to be equal to mass of potassium is 39 plus oxygen is 16 plus 1, right? And that's going to give me 56. So this is going to be 56 grams here, right? So that's gram per mole. So what we're going to say here is 1 mole potassium hydroxide, right? That has a mass of 56 grams. So therefore, we're working out for 0.352 moles potassium hydroxide, right? And we're going to cross multiply. 0.352 multiplied by 56 over 1, and that's going to give us 19.7 gram. So the concentration of the potassium hydroxide, right, is going to be equal to 19.7 gram per dm cube. Right, so I hope you all following what's happening here, right, in terms of the calculation. Right, so we've just done 2 calculations here, important because you all need to be able to do this, right? Alright, so like I said, guys, I do give online maths, physics and chemistry classes, right? Those interested, especially those entering Form 4, right, you can send me a WhatsApp at this number here, right? So those of you who are writing exam now and are calling me to find out if I have a Form 5 class right now, my Form 5 classes have ended, right? So what you are getting right now here are some material, right, especially in the month of June, for free, right? Don't send past papers to me to work. That's not what I'm doing, right? I saw somebody told me to work the January 2021 paper. All those papers were actually completed in my live online classes already. So I'm not going to be doing that here, right? I'm a past national scholarship winner, the highest mark in A-level chemistry, Cambridge, right? So I have a fair idea as to what is required for chemistry exams, right? So let's take a look at this question here, right? It's an exam question. So a student is provided with a standard solution of aqueous sodium hydroxide, right, containing X grams of sodium hydroxide in a 250 cm cube solution, right? Now, one of the things that students have to do, especially in E-level E-level chemistry, you have to make up your own solutions. At the CSEC level, you're going to the lab and they will tell you what the concentrations are. You don't have to make up anything. So in the school, they give you the solutions already made up, right? But what you have to do when you reach into Form 6, you have to make up your solutions in some instances. So this one here, they added X grams of sodium hydroxide to a 250 cm cube solution. So we have something called a volumetric flask, right? And that's what we use to make up our solutions, right? In order to determine the mass of sodium hydroxide used, he titrated 25 cm cube portions of the solution with 0.025 mole per dm cube sulfuric acid and a suitable indicator, right? Now, what they've done here, they've given us pictures, right, of our burette, right? So you see you have initial reading, final reading, initial reading. So they did the titration 3 times. Typically, that's what we do with a titration. We do it more than once. The first titration is called our rough titration because we don't know where the endpoint is in the titration. So we there performing the titration, waiting for the color change, and you might miss the endpoint because you there mixing, you're not paying attention, and all of a sudden you see the color change. So what you do, the first titration is what we call a rough, and you could discard that reading if you made a mistake. So the rough is to give us a ballpark figure. So let's say you saw a color change around 25, 26 cm cube, you know, well, alright, this is what I'm looking for. So when you do this titration a second time, you're going to slow down because remember the pipette, the burette has a tap, something you could turn on and off. So when you see you almost reach what the rough value was, you're going to slow down your burette, right, until you get the end point. And then you can do the titration a third time. Typically, that's what we do. We do the titration at least 3 times, right? So they've given us some pictures of what is seen on the burette. Now let's see what they want here. Describe the process involved in preparing a standard solution of aqueous sodium hydroxide, right? Now, like I said, I told you all what a standard solution is. A standard solution is a solution of known concentration. So you know what the concentration is, right? That's what standard solution means. So if you see that in the exam next month, that's what it is, right? So it's a solution of known concentration. And how do you make it up? Basically, we have something called a volumetric flask, right? Now I can't draw too well, right? But volumetric flask looks something like this, right? And there is a marker here, right? And when you reach that marker here, so the volumetric flask has a specific volume. So in this case here, this volumetric flask has a volume of 250 cm cube. To make a standard solution of the sodium hydroxide, what you're doing, you're going to take, so you have in the lab we have something called an electronic balance, right? So the electronic balance looks like this, and it has some numbers, right? I just drawing something here, right? This is an electronic balance here, right? So what you would do, you would take some sodium hydroxide is actually a powder. So you're going to put some sodium hydroxide inside here. So this here is sodium hydroxide. And what you're doing, you're actually determining the mass of sodium hydroxide. Now we don't know what its value is here. So they're saying it's X grams. We don't know what it is. You're going to take that X grams and you're going to put it inside your volumetric flask. So you have X grams. You're going to put it inside here. And then what we're going to do, we're going to add distilled water until we reach the marker, right? That's how you're making up the standard solution. So you have your volumetric flask. You're going to put X grams of the sodium hydroxide inside of the volumetric flask, and then you're going to make it up with distilled water, right? So you're going to pour distilled water until you reach the marker, right? When you finish with that, you close it and you're going to shake it up, right? When you shake it up there, the sodium hydroxide is going to dissolve, and what you have just done is created a standard solution, right? So that's it. That's how we make a standard solution. we need to weigh the mass of something, right? We need to take that something, put it in a volumetric flask, and then add distilled water to the volumetric flask. You shake up, and that's it. You have a standard solution there. Alright, so some of you, let's see what you are asking here, doing any AdMaths live sessions. I doubt I will do any. I have done some videos on, I think it was differentiation, I believe. There are several videos on the Maths channel, you can find them, right? I think I did probably about 6 years past papers on differentiation questions. Physics will be, today's what? Today's Chem, physics is Wednesday, right? Somebody asked about physics, physics will be Wednesday. And those of you who might be dropping in for maths tomorrow, I may be starting a little later than 3 o'clock, right? And somebody says they have to go to Spanish oral practice now. The session has been recorded, guys, so you all can get access to it after, right? So that's it for my standard solution. Now let's see if we can tackle the other parts now. So in figure 1, it shows the initial and final volumes of the burette. We want to complete the table. Now, in the exam, they give you plenty marks for this, even though you're only seeing 3 marks here, right? I've seen where they give you something like 9 marks to work these things out. So here's what we do. We're looking at, this is my first titration here, right? This is my initial, this is my final, right? Now, usually, how the burette is, the smallest value is on top, so 0 is on top in the burette, and as you go down, right, the volume increases, as the markers on the burette, right? So this is my initial value. So what we do, we usually put the final value first in our table, right? Let me ask you all something. What is my reading here in this final? For titration 1, I want you to tell me what is that reading there. Alright, so I see somebody saying 28.4, right? Let's see if that's correct. Yep, I'm seeing 28.4. Now there are some students, they make a mistake and they read the thing this way, you know, right? So be careful, it is 28.4. But here's how you're writing that in the table, eh? Now that's your final. So what you're going to do is 28.40. Please, it needs to be given to 2 decimal places. Don't just put 28.4, right? So keep that in mind. You have to put 28.40, not just 28. Be careful with that, eh? CSEC complains about that. So that's my final volume. My initial volume. What's the initial volume? Right? So you all give me a better answer here now. I see you all give me to 2 decimal places. So get into the habit of doing that, right? So this here is 3.1, 3.2, 3.3. So it's 3.30. So my reading here is 3.30, right? To figure out the volume used, right? You're going to take 28.4, right? Subtract 3.3. And what I'm going to get here is 25.1. So this here is 25.10, right? So that's my reading for my first titration. So I'm going to try to do this one a little faster now. So this one here, so let's just, this initial reading here is going to be 8.20. So this here is 8.20. This next one here is 33.20. So this here is 33.20. I'm going to read off all of them one time. This one here is going to be 6.60. and this one here is going to be 29.80. So this here is 29.80, right? So I need to take that information and put it in the table. So 33.2, 8.2. 33.20, 8.20. And the last one was 29.8 and 6.6. 29.80 and 6.60. 29.8, 6.6. Right? So to get the volume used for each of the titration, we just do a subtraction. So 33.2 minus 8.2, and you're going to get, in this case I'm getting 25.00, and then the last one, 29.8 minus 6.6, I'm going to get 23.29. Sorry, just not. We just double check our last value here, and something looking not too right here. That's 6.6 and 29 point. Yeah, so 29.8 and 6.6, right? So are you all okay with the values in the table? Alright, cool. Right? So just a reminder guys, so if you haven't done so as yet, make sure you subscribe to my channel and also hit like, right? And you can forward this to anybody you want, right? That's fine. Go ahead and forward the channel to anybody you want, right? Okay, so that's my table, right? CSEC gives you a lot of marks for these things, guys. So what do they want now? They said using the best two values from the table, state the average volume of acid to be used. Now let me tell you all something one time. This is something that students need to be aware of. So whenever you're doing a titration, right? Now some students, here's what they think. They believe that when they ask you for the average volume, what they do, they take all three values and divide it by 3, right? I want to tell you this from now, that is not always the case, right? So those of you who hear the word average and you think, here what, I'm going to add up the 3 of them and divide by 3, that is incorrect, right? You have to actually look at the data first. So let's look at this table here. Now, to be able to use, like let's say 25.1 or 25.0 or 23.2, we need to compare these values, and the values must only be different by plus or minus 0.1 for us to use it. That is important here, right? So if you've never seen this before, the values must only differ by 0.1, right? Now if you look at the first value is 25.10, the second value is 25.00, but the third value, something wrong with that value. I'm getting 23.20. That is way off compared to the first two, right? So therefore, I'm going to ignore that third value, right? Now this is the reasoning that you're using, and CSEC expects us to do that. So you're looking at the data, and you have to decide which values I'm going to use in order to work out the average, right? So the 25.1 and the 25.0, those two are different by 0.1. So therefore, I'm going to use those two values in order to determine the average volume to use. I am going to ignore the last value, right? So if you think I'm talking craziness, this is the truth. This is what CSEC wants. This is how they give marks for these questions. So what you're going to do, so in this part here, when they said, and look, they said so, they said use 2 values from the table, using the best 2 values. So the best 2 values will be the first one and the second one. So that will be 25.10. So this is what you're doing. 25.10 plus 25.00, and you're going to divide that by 2, right? So we're ignoring the last value. So that's 25.1 plus 25 divided by 2, and you're going to get 25.05 cm3, right? That's what I'm going to use. So this is what I'm going to be using in my calculations. If I do have calculations in the question, that's the volume of the acid we're going to use, right? And remember, the acid we used in this question here was, what else we used? Sulfuric acid, was it? Yeah, sulfuric acid, right? So that's the acid that we use here. We use sulfuric acid, right? That just to keep, you need to be aware of what you're doing in these questions, right? So if you see me writing sulfuric acid or sodium hydroxide, that's for me to know where I'm at in the question, right? Now, they said identify a suitable indicator. You have several indicators you can choose from. You can use screen metal orange, phenolphthalein, right? So typically in a titration like this, you'll probably use something like metal orange or screen metal orange. And then part B, explain how you will determine the endpoint. Well, basically, when you put the indicator in the sodium hydroxide, it is going to be a particular color, right? When you keep adding acid to the sodium hydroxide, right, the color is going to change at the end point. At the neutralization point, there's going to be a color change, right? Because at that point, you're going to have a slightly more acid inside of the mixture. So therefore, the color of the indicator changes, right? So you all need to be familiar with certain indicators, right? And I'm hoping you all had some labs, hopefully, right? Now they said write a balanced equation for the reaction between sodium hydroxide and sulfuric acid. Look at this, 2 marks. So let's go. This is similar to what we did previously. So sodium hydroxide, aqueous, right, plus sulfuric acid, H2SO4 aqueous, right, produces, and this here is, we're going to get salt. In this case, the salt is going to be sodium sulfate, Na2SO4 aqueous plus H2O liquid, right? That's my equation. However, notice what they have here. They have balance and they have it in bold. If you don't balance it, you're not going to get the full 2 marks. As it stands, the equation is not balanced. So what I need to do, I need to put a 2 here and I need to put a 2 here in order to balance this equation. This equation is similar to the one we did in the second question with the potassium hydroxide, right? So 2 marks, as it is here, this equation is balanced. Now, let's look at the calculation now. Okay, this is the part that gives students trouble. So they want to know the number of moles of sulfuric acid used in the titration. So let's go back to the question. What do we know? Alright, so we knew the concentration of the sulfuric acid. It was 0.025. So let me just put that somewhere here. So the concentration of the sulfuric acid, H2SO4, right, was 0.025 mole per dm cube, right? That was the concentration of the oh wait, I write it in the wrong place, yes. Concentration of the sulfuric acid, 0.025, right? So make sure I'm correct, right? 0.025 mole per dm cube. So you know the concentration of the sulfuric acid. In terms of how much sulfuric acid we use, that was the purpose of the titration. You see all of these things that you're working out here. This is the volume of my acid. But when you do the titration, they usually ask you for the average volume. So this is what I'm going to be using in my calculation, that 25.05. So what we're going to say, so look at the concentration is going to be 1000 cm cube of the sulfuric acid, right, contains 0.025 moles, right? Therefore, you're going to use the answer you got before, which is the 25.05. So this here is going to be 25.05 cm cube of sulfuric acid contains, and you're going to cross multiply. So just like we did in the previous questions, 25.05 multiplied by 0.025 over 1000, and you use the calculator to work that out. So I'm going to just use my calculator that I have here. 25.05 multiplied by 0.025 divided by 1000, right? And you're going to get a really, really small number. So what I am getting here is So you all try to work it out and see if you can get the same answer for me. 0.000626 moles. Right? Just let me know if you all get the same answer. Some of you all may write your answer in standard form. If you do, it's going to be 6.26 by 10 to the power 1, 2, 3 minus 4. Right? So either you put this or this. Just let me know if you all get the same answer before I work it out. Alright, so I see Jada got the same answer that I got, so we're cool with that, right? I'm okay with that. .05 multiplied by 0.05. Alright, so you all getting the same thing like I got, right? Alright, so that's my answer for that part. Let's see what else we need to do now. So they want to know the number of moles of sodium hydroxide in 25 cm cube of solution. Now remember, the sodium hydroxide is what we didn't know what the concentration was. Now this is where the mole ratio is coming into play. So remember, the equation looked like this. It was NaOH, right, plus sulfuric acid, H2SO4, produces Na2SO4, right? So we have to put in 2 here, and this was 2H2, right? So what's happening now? We want to figure out how many moles of the sodium hydroxide we have in 25 cm cube. Now, according to this equation, 2 moles of sodium hydroxide react with 1 mole of the sulfuric acid, right? So what we're going to do, we're going to say 1 mole, right, H2SO4, right, reacts with 2 moles. Oh wait, sorry. Yeah, no, okay, that's correct, 2 moles NaOH, right? I thought I was writing it wrong. So therefore, you know how much sulfuric acid we had, which is the answer we just got, which is this number here, 0.000626. So this here is 0.000626 moles H2SO4 should react with. All we need to do is to take that number and multiply by 2. So you're going to put 0.000, what is it, 4 zeros or 3 zeros? I'll make sure. Alright, so it's 3 zeros, right? 626 multiply by 2 divided by 1. So this answer here is going to be 0.000626 multiplied by 2. And what I'm going to get here is 0.00125 moles. Right? So this is the number of moles that actually is in 25 cm cube. Right? Hope you all follow that. All I did there was use the mole ratio in order to do that. Right? Right? You all can put, it can be, you can put in 2 here, or you can leave it out. So it's 0.001252, right? That's fine. Now the next part, remember you made up a standard solution. So you know that 25 cm cube, right, which is how much we had pipetted out, right, of NaOH, right, contains that number we just got, which is 0.001252 moles, right? Therefore, we need to work out for 250. So therefore, 250 cm cube of NaOH contains right? And you're going to cross multiply. So it's going to be 250 multiplied by 0.001252 divided by 25, and that's going to give me so what you're going to get here is 0.01252 moles, right? So that's the number of moles of sodium hydroxide in 250 cm cube. Let's see what they want now. So the last part now, they're trying to figure out the mass of the sodium hydroxide added to the 250 cm cube of water. Remember at the beginning they asked you how you make up the standard solution, and they told you that we added X grams to 250 cm cube. So what you're really doing in the question is trying to figure out what is that X, what is that value for X. So all you need to do, right, they gave you the relative atomic masses, that's important. So NaOH, right, is equal to 23 plus 16 plus 1, and you're going to get 40, right? So what that means is that 1 mole, right, NaOH has a mass of 40 grams. So all you need to do now is to work out the answer you just got, which was 0.01252 moles NaOH has a mass of, and you cross multiply, right? So you're going to take the 0.01252 and multiply by 40 divided by 1. So when you work out this here, that's going to give me what the mass is supposed to be, right? So what they actually added, that value for X is 0.50 grams, right? So the value of X in this case here is 0.50 grams. So I'm actually getting 0.5008, but I'm just going to put it as 0.50. Alright, so this is one way they can ask a question on titration, right? There are many other ways they could ask a question, by the way. So here's another one here. Now, one way of doing a titration, like we did previously there, we can use a pipette, and a burette, right? And we can find the endpoint using our color change, right? So using an indicator to determine the color change. Now, hopefully you all may have done this as a lab in school, right? So they said it is possible to determine the endpoint of an acid-base titration by measuring temperature changes, right? So when we use temperature changes to do a titration, that is called a thermometric titration. And what we're doing, we're using a thermometer in order to do that, right? So what we would do is we would be adding, let's say, what are we doing here? We're using, right, so these are my solutions. This is sodium hydroxide. And then we're gonna add sulfuric acid to it. So what's happening here? You have basically a styrofoam cup, right? So this is a lab that hopefully you would have done, right? And in the styrofoam cup, you have 25 cm cube. So you have 25 cm cube of NaOH. That's what you have here inside of the cup, right? And then we're gonna keep adding. Well, first of all, you're gonna put a thermometer inside here, by the way. So you have a thermometer here. And then you're going to keep adding some acid to the sodium hydroxide. In this case, what are we adding here? Sulfuric acid. So you're adding sulfuric acid to this, right? And every time you add the sulfuric acid, you measure the temperature. So for when you have no acid is added, the temperature of the solution was 22.5. Then you come and you added 3 cm cube, and you got a new temperature of 29.5. You added 6 cm cube, and then we got a new temperature here, right? So the more acid you add, the temperature change is being measured every time. So let's see what they want us to do. So, right, so if you notice in the table, you're missing two values. You're missing this value here for temperature, and you're missing these two values here for temperature, right? I want you all to read off, tell me what is this first temperature value here. What is that temperature reading? Right, so if you all never saw this before, this is called a thermometric titration. Right, I've seen everybody getting 41 degrees. Let's see if that's correct. Let's see if that's correct. So this one here, now you have to look at the scales, right? So this here is 41, right? So every small marker is 0.1 of a degree. So this is actually 41.0 degrees Celsius. What about the second one? What's he reading on the second one? Alright, I see you all saying 25. Let's see if that's correct. So, if this is 24.5, that means that here is 24. That means that here is 25. Right? So, they try to confuse you a little bit here, but it's really 25 degrees. So, this here is 25.0 degrees. Right? Celsius. Right? So, the temperature readings, they go to 1 decimal place, right, based on the accuracy of the thermometer, right? Direct, we can go to 2 decimal places, right? So let's put those figures in the table. So this here is going to be 41.0, and this next value here is 25.0. So this is 25.0. Right, so the next thing, what they want us to do now. First part, differentiate between a strong acid and a weak acid. Guys, you all need to know the difference, right? A strong acid is completely ionized in aqueous solution, right? So a strong acid, that's the definition that CSEC wants, and nothing else. Don't make up anything for the people. You won't get any marks. So it's a strong acid is one that is completely ionized in aqueous solution. Right? That's your definition. That's what a strong acid is. So strong acids are things like sulfuric acid, hydrochloric acid, right? This one here, when they ask you what is a weak acid, a weak acid is partially ionized in aqueous solution. So like I said, these are the answers that they want. Don't go and make up something that is incorrect. So it's partially ionized in aqueous solution, right? And if they give you plenty lines, what you could do, hydrochloric acid is a strong acid, and this is what happens when we say it's ionized. It produces hydrogen ions in solution, because that is what an acid is. An acid is a substance that produces hydrogen ions in solution, or you can say it's a proton donor, right? They could ask you what an acid is. For a weak acid, what we typically use, we use vinegar, or what we call acetic acid or ethanoic acid. But what happens in this case is it's a reversible reaction, and we get this CH3COO minus plus H plus. Now, you see this sign here? That's a reversible sign. That's how we know if something is a weak acid, right? It is partially ionized. That is what that sign means, right? Now, they said state one other base that could be used instead of instead of sodium hydroxide. Well, our next base we could use is potassium hydroxide, right? That's our next one we can use. Now, the third part, they said using the thermometer readings in figure 1, complete table 1 by recording the temperature. So we did this already. We read the thermometer and we completed the table, right? Plot the points of temperature versus volume of acid added using the axes on the page, right? So they want us to plot the points, and then they said draw two lines of best fit, right? Where the temperature is increasing, where the temperature is... Okay, so I'll show you what we need to do here. So what we're doing, we're going to draw a graph, right? So I hope you all see in here kind of small-ish, right? So let's see. Our first reading will be, let's see first reading here, 0 against 22.5. Now they helped us out here. They put in the numbers for us, right? Which is a big help in the exam. So the first value is 0 against 22.5. So you need to make sure you know how to read these things, eh? So 22.5. So we need to understand our scale first of all. So from here to here is 5, which means that every 2 line is actually 1. Every 2 line is actually 1 degree, right? So if you want to get 22.5, that's going to be 21, hold on, 21, 22, right? So 22.5 is actually this point here, right? That's 22.5. The next point we're going to plot will be this one here, right? Which is 3 cm cube against 29.5. So 3 cm cube against 29.5. So 3 cm cube is somewhere in the middle here, and 29.5 is here. Alright? Now I know you may not see the graph properly, but just understand the concept itself. The next one here, we're plotting 6 against 36. So you're going to plot 6 against 36. So 6 here against 35. Right? That's 36 there. 6 against 36. Next value we're going to plot here will be 10 against 41. So you could get a question like this in the exam. Eh? 10 against 41, that is going to be 40. This is 41 here, right? Hope that's correct. 10 against 41. The next value we're plotting here is 15 against 38. So 15 against 38. So the temperature is on the drop now, right? 15 against 38. This is 35, 36, 37. That's about here, right? Next point I'm going to plot is 20 against 25. So 20 against 25 will be this value here, right? This is 20 against 25, and the last value is going to be 25 against 13.5. So 25 against 13.5. So this is 25 down here, and you want to get 13.5. So 10, 11, 12, 13. So 13.5 is about here. So all I've done here is plotted the points, right? This is typically how the graph looks, guys, right? So I'll show you how we're going to get the endpoint from this graph. Those of you doing chemistry privately, this could come as a question in your paper, by the way, right? Those of you doing it privately who have to do the paper 3. Now, let's see what I'm going to do. So the question says, now please, when you're doing a thermometric titration, do not go and draw a smooth curve. If you do that, CSEC is going to penalize you, right? Do not go and draw a smooth curve. What you're doing here, look at what it said. You want to draw 2 lines, so they're telling you what to do, they're guiding you here. 2 lines of best fit, where the temperature is increasing and where the temperature is decreasing, and hence determine the endpoint. So here's what we have to do. So let me get some lines here. here a little line that's a little thicker. Right, so I have 2 lines here. Right, now what they told us, told us to draw, so you're gonna take your points where it's increasing and you're gonna draw a line of best fit. Right, now a line of best fit is a line where most of our points, right, pass through that line. So look, my first 3 points, they kind of line on that straight line there. So that's my first line that I'm going to draw. The second line now, right, we're going to take that second line and we have to draw it through the rest of the points, right, in such a way that, so we're going to have to do something like this, right, where it kind of passing through our points here, right. Now let me see this point here. I might have to adjust this line a little bit, right, this one, because our temperature is still increasing here. So right, so this is what I'm going to use. So what you need to do, you need to draw 2 lines, one for when the temperature is increasing and one for when the temperature is decreasing, and where these 2 lines intersect, right, that is where I'm going to get my endpoint. So you're looking for the peak where those 2 lines intersect, right? So I know some of you all may not have seen this before, but this is required. You all need to know how to do this. Right? Let's make this line longer. So what you're going to do, you're going to come to the graph and you're going to read off where that peak is. Right? Now, according to my graph here, right, I'm getting something like, what is that there? That's 10.4, 10.8. Right, that is about 11.8, right, about 11.8, around there, right, that's the volume I'm getting, right. So what you're doing, you're just reading off this value here. This value here is what I'm reading off, right, here, this value here, right. So you need to be able to read that value. From that graph there, I'm getting 11.8. So the answer for here is going to be 11.8 cm3. Right? So this is one way we can find the endpoint of a titration, right? And this is what we call a thermometric titration, guys, right? Yeah, so we're looking, so somebody's asking something there, right? Basically, we're trying to find the volume that gives us our highest temperature. You see, if you had drawn a curve passing through the points, you would have gotten the volume wrong. So we use the 2 lines, we construct the 2 lines in order to actually predict where is our peak on that graph. That's what you're doing. You're trying to find where is the peak, right? So you're not drawing a smooth curve. The tendency for students to draw a smooth curve is high. They want to draw a smooth curve, right? That's not what you have to do in this particular question. You're drawing 2 straight lines, and where they intersect, that will give us our maximum temperature, and we're going to read off the volume that corresponds to this maximum temperature, right? So in this case here, I've gotten 11.8. Next thing they want a balance equation. If we go back to the question, we were mixing, what were we mixing? Sodium hydroxide and sulfuric acid. So this is sodium hydroxide, NaOH, please use the state symbols here, plus, and they want a balance. Notice they put the word balance in bold, eh? So it's 2 NaOH plus H2SO4 aqueous, right? And that's going to produce my salt, which is Na2SO4 aqueous, right, plus 2H2, right? So that's what's going to happen here. Next thing they want now, they want the number of moles of sodium hydroxide used in this reaction, right? Now let's go back here. I can't remember what they said about the sodium hydroxide. So, okay, so this information is pertaining to the sodium hydroxide. It's 2 mole per dm cube and it's 25 cm cube we use. So the sodium hydroxide was 2 mole per dm cube, and we used 25 cm cube, right? And we want to figure out how many moles we use. So all we need to do, we need to say 1000 cm cube, right, of NaOH contains 2 mole, right? Therefore, you want to work out for 25. So 25 cm cube of NaOH contains, and we cross multiply. So it's going to be 25 multiplied by 2 over 1000, and that's going to give me, that's 50 divided by 1000, and you're going to get 0.05 moles, right? So 1 mark for that. And the last part, they want us to work out the concentration of the sulfuric acid. So here's what's happening here. You know the mole ratio. According to this equation, 2 moles of sodium hydroxide should react with 1 mole of sulfuric acid, right? According to the equation. So 2 moles, so let's see, 2 moles of NaOH reacts with 1 mole sulfuric acid. That's from the equation. Equation told us that, right? Therefore, in terms of moles, the amount of moles of the sodium hydroxide we used was 0.05, right? 0.05. So we're going to say 0.05 moles NaOH reacts with, and you're going to say 0.05 multiplied by 1 over 2, right? So that's 0.05 divided by 2, and that's going to give me 0.025 moles of sulfuric acid, right? So this is the number of moles we had at the end point here. But the thing is, based on the answer we got here, this was the end point of the titration, 11.8 cm cube. So what we're going to say now is 11.8 cm cube, right, of the H2SO4 contains, that answer we just got there, contains 0.025 moles, right? Therefore, if you're working on concentration, we need to work out for 1000. So it's 1000 cm cube of sulfuric acid, H2SO4, contains, right, and you're going to cross multiply. So it's 1000 multiplied by 0.025 over 11.8, and that's going to give me and you're going to get 2.12 moles, right? So therefore the concentration of the sulfuric acid, H2SO4, is 2.12 mole per dm cube, right? So that's my concentration of my sulfuric acid. Right, so Sadiq is asking me if we could use a fraction. Try to work in decimal for most of these questions, right? Try to work in decimals, right? So based on what they told us in terms of the broad topics, chances are you're going to get an acid-base titration, right? So what you need to be familiar with is all the calculations that I've just shown you, right? I hope that this session was productive for you guys. So make sure you know how to write a balanced equation. Go back through the video and make sure you understand why I did certain things in the calculations, right? Remember, the first question is 25 marks, and things they can ask you in the first question could be, what is a standard solution? What is a strong acid? What is a weak acid? Give me an indicator that I can use in the titration, right? You can do a titration using a pipette and a burette, and finding the endpoint using an indicator. That's one way you can do a titration. There's another way we can do a titration. It's called a thermometric titration. That's what I just did there, right? So be familiar with that. right? I mean, these are things that CXC can bring, and they brought them many times in the past already. All right. So, like I said, I hope that the session was productive for you all. I hope you all learned something, right? And again, for those of you who are interested, I do give online maths, add maths, physics, and chemistry classes, right? My new classes begin in August, right? So I'm taking in a new batch of Form 4s from August, right? My existing Form 4 classes are still in progress, all right? So guys, that's it for me, and I hope that you all enjoy the class. Right, so like I said, those of you who usually attend the math session, tomorrow's session might start a little later than 3 o'clock though. Alright, so take care guys.